All right, it's 10 o'clock. How are we doing today? How'd the exam go? I guess we'll find out Friday. It's jury day. I see lots of jury faces. I'm going to pass the box of candy. Have some treats. All right, so a few things to announce. My office hours tomorrow are going to be altered a little bit, so I can be there from 3 to about 4:10, and then Melissa will be there from 8 to 10 on Friday. Friday's lecture, as is typical after the exam, that's optional. Brian will be leading it, so he'll go over the exam, talk about, what questions you might have about it. That's your opportunity to request regrades. The other thing I just want to make sure everybody remembers, the exams are secure. That means that you have to turn them back in. You can't take photos of them, etc. So if you don't follow the rules, you've committed academic misconduct. All right, so looking ahead, we've got a standardized exam coming up that's optional. That's going to be Thursday of Dead Week. And then the final exam, those of you that are registered for this section will take it on Tuesday. And those of you registered for the 110 section will take it on Wednesday. I'm going to follow the rules for the registrar for accommodations of conflict. So if you fall into any of the reasons to have it rescheduled, you want to contact me before the Friday before Dead Week, which is April 26th. Okay? All right, so things that we've talked about previously, and this showed up on the exam last night. We've pointed out that when there's a difference between the calculated entropy, that is from spectroscopic data, Q, if there's a difference between that and what we get from calorimetry data, it's always going to be that the calculated one is greater. And that's because if I do an experiment with calorimetry and I cool down my crystal, I can't guarantee that it's going to be perfect at 0 degrees Kelvin. All right. We showed that we could calculate the entropy changes of a reaction at 1 bar using standard molar entropies. And then from there, we moved into chapter 8, where we started talking about spontaneity. And one of the things that we didn't explicitly state, but we showed the reason that we use the Gibbs energy and the Helmholtz energy as criteria for spontaneity. We wanted something in terms of the system variables. And basically what we found is that delta G and delta A are both equal to minus temperature times delta S of the universe. Right? And this equality holds true for delta G when we're talking about constant pressure, constant temperature processes, and it holds true for delta A for constant volume and constant temperature processes. So what we're going to do today is we're going to continue our discussions of Helmholtz and Gibbs energies. In the chapter, we're going to be seeing how they're useful. And of course, some of this overlaps with what you've seen from Gen Chem 2, where you were introduced to delta G, right? We'll see along the way that there's a physical significance between delta A and delta G. There's something that's critical with respect to work for those. We're going to introduce something known as Maxwell equations. How many people have heard of Maxwell equations before? All right, because these could be a little bit of confusing, we're going to do a little bit of advanced exposure to Maxwell equations before we get into the lecture. We've talked about natural variables again. That shows up a lot with Maxwell relations. And then from there, we're going to look at entropy's dependence on volume and pressure and the energy of a system. I'm not sure we'll get this far today or not. All right. So at any rate, in the last chapter, we derived this expression. We've seen this before. What I can conclude from that expression is that entropy depends on temperature and it depends on pressure. So S is a function of temperature and pressure. Now, if I look at the total differential, that says this first term is the same as ds dt, and the second term is equal to ds dp. We've pointed out those aren't simple variables, and therefore we can't say that those are natural variables, right? So what we've previously pointed out is looking at du, we've shown that that's equal to TdS minus PdV. Okay? All right. And using the same, same logic, we can say then that this equation tells me that U is a function of S and V. All right? And this first term is du ds holding V constant. The second term is du dp holding S constant. Okay? And then we look at these derivatives and we say that's a simple function. That's a simple function. And so what we can conclude from this is that S and V are natural variables. For entropy, or of U, sorry, of the energy of the system. Okay? Yeah?
How come it's dV? I mean,
du, dv, yeah, yep. Have more candy. Did the box make it anywhere other than that table? Yeah, okay. All right. Sorry. Okay, so that's all review, all right? What we're going to introduce now are Maxwell relations. At the outset, we need to define what they are. And they are the cross derivatives for these differential equations. Right? So they're cross derivatives. And so for this particular example, we've established that du ds is the same as t. So if I want to take the cross derivative, that's going to be dt. Help me out. What am I going to take the derivative of that with respect to? dv. All right. And then I hold s constant. All right. And then if I want the cross derivative for my second term, that's going to be the derivative of minus p with respect to s. All right. The derivative of p with respect to s, now holding the volume constant negative, right? Okay, so here I've taken the cross derivatives, right? And the thing that where this becomes important is we know that u is a state function, right? That tells me that this is an exact differential. And if I have an exact differential, what's true about the cross derivatives? They're going to be equal to each other, right? So this is an example of a Maxwell relationship. Right? And then we say, well, what's the significance of that? All right? So the one thing that we can see is that we have an identity. dt dv is the same as the negative of dp ds. Right? Now, if I told you to go into the laboratory and measure one side of this equation, which side would you choose to measure? The left side, right? Because you can easily measure the relationship between temperature and volume in an experimental setting. It's not so easy to measure dPds, right? So what this does is it gives us an identity that gives us an expression for a quantity that we can't directly measure in terms of something that is measurable, right? And that makes these powerful, right? So these yield equations or identities that relate thermodynamic properties to measurable thermal properties. Okay? All right, and then the other thing that we can do is we can recognize that once I have this equality, I can rearrange it and say pressure depends on ds, or ds depends on pressure, right, by rearrangement, right? And so this allows us to determine how how thermodynamic properties change, right? And we'll do some applications of that, okay? All right, so the last time we met, where we ended was we started with the first and second law, and we combined them together, and we took our understanding that this quantity du minus tds is going to be less than or equal to 0, and that allowed me to create a new function, u minus ts, that determines whether something's spontaneous or at equilibrium or not. So because this is true, gave rise to saying, all right, I'm going to let the energy minus T times S be what we call the Helmholtz energy. All right? And now I get a criteria for spontaneity for constant volume, constant temperature that depends only on the system parameters. Right? So that's what we've said previously. Now if I come back to this relationship here, A equals U minus TS, we can do the differential and integrate that and get delta A is equal to delta U minus, so I'm going to write delta TS would be equal to TS final minus TS initial, right? And if I hold the temperature constant, that comes out in front and it becomes T delta S, right? So I can say that the change in the Helmholtz energy is given by the change in the energy of the system minus T delta S, as long as we're holding the temperature and the volume constant, okay? All right, so this equation is going to be important as we will see momentarily, all right? So now I think about a reaction or a process that we perform, all right? We know for delta A, for the process to be spontaneous, delta A has to be less than 0, right? That's what we've shown previously. So let's look at the possibilities. Let's say I have a process that produces heat. That means delta U is negative, right? Just a reminder, delta U is the same as QV, okay? And let's say I also have a process that the system's entropy goes up. So that's positive, all right? Now, if you think back on what we've been talking about, the fact that I'm going from a higher energy state to a lower energy state for my system and releasing that energy difference as heat suggests that it's going to be spontaneous. And we've also know that entropy for spontaneous processes tends to be positive, right? So if I have a negative delta U and a positive delta S with this positive temperature, this is always going to be negative, this is always going to be negative, so what's delta A going to be? It's always going to be negative. And that tells us we don't have to think further. If my process produces heat and the system itself is accompanied by the change in that system causes an increase in the entropy of the system, we know it's going to be spontaneous. So we can say always. All right? And of course, we can look at the opposite side of that. If I have a process that requires the input of energy and the process itself's entropy change is negative, then I know that delta A will always be positive and it will never be spontaneous. Okay? All right, and here I just need to make sure that we talk a little bit about this. So keep in mind, spontaneous means left on its own will occur in this direction. I can make a non-spontaneous process occur by coupling it with another process, right? Does that make sense? Okay. All right. And then we can look at the mixes. So I can have a process that requires the input of heat and also is accompanied by an increase in entropy. All right? So that's saying this term is positive, and then the negative of this term will be negative. So this really depends, delta A depends upon one variable, right? I can have a positive or a negative delta A, all right? So if I want this to be a spontaneous process under these circumstances, which term, delta U or T delta S, has to be larger? The T delta S term. And that's going to occur at what temperatures? Large temperatures, right? Okay? So this says that I have a process that is going to occur at a high temperature, and then if I go to a low temperature, it's not going to occur. All right? And if I have a positive delta A at one point and a negative at another point, you know that it's going to have to pass through what value? It's going from positive to negative. What value does it have to? It has to pass through 0. So there's going to be a point at which it's going to be at equilibrium, right? So we'll talk about that a little bit down the road with respect to delta G. And then the other side of it is I have a process that produces heat, so it goes from a high energy state to a low energy state, but also is accompanied by a decrease in the entropy of the system, right? And for the same reasons that the last one gave us positive or negative values of delta A depending on the circumstances, in this case we expect the process to be spontaneous whenever the first term dominates, right? That's the one that's contributing towards spontaneity. And that means that we expect this process to be spontaneous at what kind of temperatures? Low temperatures, right? Okay, so the other thing we want to do is just think about if we have a system and we're performing this process at constant temperature and volume, we expect that it's going to go in the spontaneous direction, and that's going to occur with A decreasing. Right? And that's going to continue to decrease until the process isn't changing anymore. That means I've arrived at equilibrium. Right? So until A is minimized for the system, and that's going to occur at equilibrium. And what's dA going to be equal to at equilibrium? That's going to be equal to 0, right? Because our criteria for spontaneity is dA is less than 0. Our criteria for equilibrium is that it's equal to 0, right? And then graphically, we can show that for constant V and T process, the Helmholtz energy is a function of time. We'll start out at some initial value, I'll just call A naught, right? And whatever process occurs, it's going to decrease until that time where dA is equal to 0. I have equilibrium, and A is minimized. Okay? Does that make sense? Okay? All right, so let's look at an example of something that we've seen previously. So when we've talked about isothermal mixing of two gases, we showed that delta S for that process per mole is given by the mole fraction of the gas phase times R ln of the mole fraction of the gas phase with these. So we've derived this expression, right? Let's see what happens to that if we want to put this in terms of the change in the Helmholtz energy. Right? Now, because it's an isothermal and because it's ideal, we know that there's no interactions between the particles. So delta U is going to be equal to 0. Right? And then I've got delta S, and I need to multiply that by minus T. So that's going to be minus a negative T y1 R ln y1 plus Ty2 r ln y2. Okay? All right, so all I've done is taken this expression and multiplied it by minus t. Okay? And then if we look at this and say, what does this give us in terms of the sign of delta A? Well, we know that yi is between 1 and 0, which means the natural log of yi will be, help me out, it's going to be less than 0, it's negative. And r and t are positive. This is between 0 and 1. That tells me this term is negative, this term is negative, so the whole thing is negative. Okay? Right? And so this is consistent with what we've seen for delta S, and this is what we would expect to spontaneously occur. Therefore, delta A has to be less than 0. All right? Okay, so next up, what we want to do is look at the relationship between delta A and work. Right? You may recall last time that I said that the Helmholtz energy symbol is from Arbeit, the German word for work. Right? So we want to take a moment to see if we can get that relationship. Right? So what I'm going to start with is, our definition. Delta A is equal to delta U minus T delta S. This we know is true as long as we're talking about constant temperature and volume. Right? And then the other thing that we know is that the definition of delta S is going to be, let me go through this step by step, the integral dq reversible over T. Right? Now, what we've said is that we can use this equation as long as temperature is held constant. That means I can pull that out in front of our integral, and then we're integrating dq, so that means that my result is going to be q reversible over T. Okay? All right, so that means I can say that delta A is equal to delta U minus T times q reversible over the temperature. All right? And pretty straightforwardly, we see that temperature cancels with temperature. And if you go back to the first law, what's the difference between delta U and QW, or Q reversible? It's going to be equal to the reversible work. Okay? All right, so what we can say is that W reversible is the same as the change in the Helmholtz energy. So this gives us a good physical interpretation of what's meant by the Helmholtz energy. So if we have a delta A, that tells us that's the maximum work I can get out of that spontaneous process. Or if it's a not spontaneous process, if I want to drive it forward, that's the minimum work that I have to dump into it to get the process to occur. All right? Okay, so then just talking about this same thing symbolically, if W is less than 0, that means our process is performing work. Under those circumstances, what we expect is that the real work, absolute value, will be less than delta A. Okay? And if we have to drive the process forward, then the situation is if work is greater than 0, then we have the absolute value of the real work is going to be greater than delta A. Right? But it gives us our limiting work that we need that's associated with the process. Okay? All right, any questions about that? All right. So what we've done so far is get a relationship between work and Helmholtz energy changes, and we've shown why we have this definition of the Helmholtz energy for a constant temperature and volume process. So we're going to do the same thing now, but looking at constant temperature and pressure. So a constant temperature and pressure it's going to be the sign of dg or delta G that determines spontaneity. Okay? All right, so we do a very similar thing that we've done previously. We start with our first law. We say du is equal to dq plus dw. And then the second law, the inequality of Clausius, tells us that dq is less than or equal to TdS. And so that means I can plug this in for dq, and that gives me du is less than or equal to TdS minus PdV, assuming that we have only pressure, volume, work, right? And then what I can do is I can rearrange this and say du minus TdS plus PdV has to be less than or equal to 0. Okay? And so I have a differential on this side, and then I can say, well, I'm going to take a differential of the total function, right? So that's going to be the same as du minus TS plus PV is going to be less than or equal to 0. Right? And this is true, this is in agreement with this, as long as I'm holding my temperature constant. Okay? Right? And so this allows us to define the Gibbs energy as U, as this quantity in the parentheses. So I'm going to do a little rearrangement here. It's going to be U plus PV minus TS, right? And you may recall that U plus PV is the definition of enthalpy, right? So that means that that G is given by H minus TS. Okay? All right. And then down below, we can recognize that there's a relationship between the Gibbs energy and the Helmholtz energy. So if you remember, U minus TS was the Helmholtz energy. So that's going to be Helmholtz energy plus PV. So that gives us the relationship between the two of them. Right? I'm going to cross this out because it's just not very important. Okay? All right. So at any rate, now we have the Gibbs energy defined. Right? And then what we can do is talk about what delta G is. All right. So delta G is going to be given by delta H minus, if I'm holding temperature constant, that next term goes to T delta S. All right. So it's the Gibbs energy that we use for constant temperature and pressure. All right. So before we talk about this, let's just complete our discussion. So we've established up here that D, this function, which we now know is G, is got to be less than or equal to 0. All right? So that can be written as dG less than or equal to 0. All right? And if we're talking about a spontaneous process, dG is going to be less than 0. If we talk about a process that's at equilibrium, that's when the equality holds and dG is equal to 0. Okay? All right, so just a reminder, everything that we've done in this section parallels precisely what we did in the previous section for the Helmholtz energy. Okay? All right, and then just as we did with the Helmholtz energy, we're going to ask, under different circumstances, looking at enthalpy change and entropy change of the system itself, what can we say about the spontaneity? All right, keeping in mind that delta H is the same as QP. Okay? All right, so let me ask you this question. If I want delta G to always be negative, what does delta H have to be? It's got to be negative. And if I want delta G to always be negative, what does delta S of the system have to be? It always has to be positive. All right? So under those circumstances, delta G is going to be negative, and it's always spontaneous, right? Step back. This says I have a reaction or process that produces heat. We call that exothermic, right? And is accompanied by an increase in the entropy of the system. That will always be spontaneous. If I reverse the process, or if I have a process that's endothermic and also has a decrease in entropy for the system itself, delta G is always going to be positive, and that's never going to be spontaneous, right? So if I want to get it to occur, I'm going to have to drive the process, right? And then we look at the mixed cases. So if I have an exothermic process but a decrease in the entropy of the system, we know that delta G can be plus or minus. And at what temperature regime do we expect delta G to be negative? It's going to be at the low temperatures, all right? All right, I'm going to put a little label there, A, right? So if we step back and look at the overall process, we see that this process is going to be spontaneous when the enthalpy dominates, right, at low temperatures. We call this an enthalpy-driven process. All right? And then case B will correspond to an endothermic process, one that I have to dump heat energy into the system. I see that the system itself has an increase of entropy, so we know that delta G can be positive or negative. We expect it to be negative at what temperatures? At the high temperatures, all right? And because in this case, the term that determines whether it's spontaneous or not is the enthalpy or entropy term, right? So we call that an entropy-driven process. Right, does that make sense? All right. Now we don't label this as entropy-driven or enthalpy-driven because it's both. Right? I don't need to distinguish. It's always spontaneous. This one's never spontaneous. This one, it's mixed. And the first one is enthalpy-driven because that's what determines the spontaneity. And the other's entropy-driven. Okay? All right. So we've previously pointed out that if I have a situation where I'm either enthalpy or entropy-driven, that means there's going to be times that the process is spontaneous, and there's going to be times that it's not spontaneous, which means that I have to pass through the point at which we expect delta G to be equal to 0. Right? And if we think about that point, right, if I make an infinitesimal change in one direction, the process goes. If I infinitesimally change it in the opposite direction, it returns and goes the other way, right? What's that the definition of? That's a reversible process, right? That's the equilibrium state, right? So at that point, we can say that delta G is equal to 0, delta H is equal to T delta S, and delta S is equal to delta H over T, right? And we've seen this before, right? We've seen this for phase transitions. This also says I can do this for chemical reactions, right? Okay, so we can point out that this explains why we have the relationships that we have in our day-to-day lives for melting of ice, freezing of ice, vaporization of water, and condensation of water, right? It's all about the fact that we have a mixed situation. So if we think about vaporization, I'm going from the liquid phase to the vapor phase. What do you expect for delta H of vaporization? To go from liquid to vapor, do I have to put heat into the system or do I have to remove heat from the system? I have to put heat into it, right? So that means that that's going to be a positive value. right? So delta H is positive, right? And delta S for vaporization, well, I'm going from the liquid phase, condensed phase, into the gas phase, right? The molecules are confined to a particular volume. And then in the vapor phase, if I change the volume, they expand, right? So what's delta S? It's positive, right? So this process, you tell me, is it enthalpy or entropy driven? It's entropy driven. And when it's entropy driven, let me write delta G's equation down, right? So delta, we've got it there. So in this case, this tells us that this term needs to dominate for the process to occur spontaneously. And if it doesn't, if it's smaller than delta H, then delta H determines that the reaction goes in the opposite direction, right? And the point at which this occurs is the boiling point, right? At the boiling point, this temperature makes delta H and T delta S equal to each other, and delta G is equal to 0. Okay, and that's all stated in that portion, right? And because it's Wednesday after an exam, we have a quiz for you. You guys can work on your own on this. We're going to give you 2 minutes, right? And can you check your answer? What's the freezing point of water? 0 degrees Celsius, okay? You have 1 minute left. Yeah. I would prefer that you do that.
Yeah. You should always put. Yeah. Okay.
You should always put units. You're right.
Dorian is always correct.
Or Mr. Bean. I can't because your textbook does horribly with sig figs. So, and there's enough other moving parts to worry about in this class. So, all right. So I'm coming around to collect these. You guys done? Thanks. Thanks. Thank you. Thank you. I'll be there in a second. Thanks. Did I get yours already? Yeah. You guys good? All right. So how many of you guys are going to talk to your family today? You already talked to them? Well, next time you talk to them, you can say, hey, I proved that the freezing point of water is 0 degrees Celsius today, right? Or 273 Kelvin if you really want to impress them. All right, so the answers will be worked out on the posted annotated lecture notes. So where we're going next is just like we did previously for the Helmholtz energy. We saw that there was a relationship between delta A and work, right? So we're going to look now at what delta G tells us about work. And I want to say in advance what we're going to get this time. Delta A we saw was the reversible work that I get out of the process. In this case, delta G is going to correspond to work, but it's going to be the non-pressure volume work. All right, so we need to show where that comes from. All right, so we're going to start with the Gibbs energy. G equals U plus PV minus TDS. And I'm going to differentiate this. So dG will be given by du, right? And now I'm not imposing any limits on it. I'm going to say dPV will be PdV and VdP. Right? And then I'm going to do the same thing for temperature times the entropy. So that's going to be minus TdS minus, help me out, SdT. Okay? All right, now if I impose constant temperature and pressure, then I'm going to say dP is going to be equal to 0, so that term goes to 0. dt is equal to 0, that term goes to 0, and therefore I'm left with du plus pdv minus TdS. Okay? Now previously we've shown that du is given by TdS minus pdV. Okay? All right. The other thing that we want to just point out here is that we've made the assumption that the only work that I can have is pressure volume work. So now we're going to say we're going to let this be more general situation. So I'm going to include the reversible non-PV work. Right? All right, so let me ask a question. What would be non-PV work? Anybody? You guys all use cell phones, right? What's powering them? A battery, right? And they're doing that's electrical work, okay? And you may recall back in Gen Chem, I'm guessing in Chem 177, you saw that you could take electricity and decompose water into hydrogen and oxygen, right? Or you guys have heard of fuel cells, right? That's all non-PV work, right? Okay? All right, so putting these together, if I plug this in for du, I see that I lose PdV, I lose TdS, and dG is simply going to be equal to dW reversible for non-PV. Right? And if I integrate both sides, then I can say delta G is going to be the total work that I can get reversibly for a non-expansion compression work. Okay? Does that make sense? So back in Gen Chem, when you calculated delta G and you got a negative number for a process, that told you, given that amount of reactant, that's how much work you could get out of the system. If you got a positive number, that represents how much work you have to get into the system in a non-pressure volume way in order to drive the process. Okay? All right. W reversible, non-PV. And then we can do the same sort of thing that we did before. So if work is less than 0, that means that work's being produced by the system. And then we can say that W real is going to be less than the absolute value of delta G. And if W is greater than 0, meaning I have to do work to drive the process, then we can say W real absolute value is greater than delta G. Right? But the main idea is that delta G represents the limiting value of the work that's not pressure volume. Okay? All right, so then, just an example. So in this case, we're asking, what kind of work or what amount of work do I need to take a mole of water and decompose it into its constituent elements? So I'm going to talk a little bit about this. So we know that delta G is going to give us that answer, right? So I wanted to talk a little bit how you can calculate delta G, right? That's going to be delta G of the reaction, which we know is going to be delta H of the reaction minus T delta S of the reaction. Because we're talking about, in every case, being at 1 bar, we know that we can calculate delta H from enthalpies of formation. We can calculate delta S from absolute values of entropy. The other thing is if we go into thermodynamic data, we also find that there's delta G's of formation that are listed. Right? And this, in fact, turns out to be, I'm asking about 1 mole of water being decomposed. Well, if I make a mole of water from hydrogen and oxygen, that's going to be the Gibbs energy of formation. Right? So if I flip that, that's what I'm interested in, the decomposition of water. Right? So that tells me that if I want to drive this process, 237 joules is the minimum amount of electrical work that's needed to convert that, all right? Okay, that's where we're going to leave it today. I'm leaving you out a little bit early because you guys, I'm ahead in here a little bit because it's a dreary day and y'all look like you could use 3 minutes to charge up a little bit. All right, have a good one. Brian will be here on Friday. Scores for exams will be posted sometime tomorrow.